Hey there, YouTube watchers. This is Abigail Visitacion, and today we will have our examples of the ordinary differential equations and how to solve them. But first, what is an ordinary differential equation? Well, an ordinary differential equation, or ODE, is an equation containing a function of one independent variable and its derivative. I assume you know the ordinary differential equations of the first order, so let us proceed to the examples. For our first example, let us solve the equation xy squared minus y quantity dx plus x squared y minus x quantity dy is equal to 0. First, by integrating it as exact, and then multiplying it by 1 over x squared y squared before integrating it. Reconcile your result. We can immediately see that the given equation is exact, but just to be sure, let us check for its exactness by letting functions m and n as the first and second terms respectively. Now the partial derivative of m with respect to y is equal to 2x y minus 1, and the partial derivative of n with respect to x is also 2x y minus 1. Because they are equal, then the given equation is exact. We now proceed to step 2. We have here u is equal to the integral of m dx plus the constant ky. Substituting the value for m, which is xy squared minus y, and then integrating it, we arrive at the answer u is equal to x squared y squared over 2 minus xy plus the constant ky. Step 3. We now find the value of the constant ky. We can do this by differentiating u that we got from step 2 and then equating it to n. So we have partial derivative of u with respect to y is equal to x squared y minus x plus the partial derivative of the constant ky with respect to y is equal to n. Then we arrive to the answer, partial derivative of ky with respect to y is equal to 0. Therefore, u is equal to x squared y squared minus 2xy. Now, let's multiply both sides of the equation by 1 over x squared y squared. We then have 1 over x minus 1 over x squared y quantity dx plus 1 over y minus 1 over xy squared dy equals 0, which is, again, an exact equation. We'll check if it's really exact by doing what we did before. Here, we'll let functions p and q as the first and second terms respectively. Since the partial derivatives of each term are equal, the equation is truly exact. Step 2. We now have u equals the integral of p dx plus ky. We now substitute the value of p, which is 1 over x minus 1 over x squared y. By integrating it, we arrive at u is equal to ln x plus 1 over xy plus ky. Step 3. We will now solve for the value of ky by differentiating u that we got from step 2 and equating it to q that we got from the original equation, which will eventually lead us to ky being ln of y. Therefore, our answer is u equals ln x plus ln y plus 1 over xy, or u equals ln of xy plus 1 over xy. U equals x squared y squared minus 2xy is an exact function. As solved via integrating factor 1 over x squared y squared, u is equal to ln xy plus 1 over xy. The reconciliation of these results consists in observing that each of these solutions is one of the form f of xy equals constant, and noting that this implication of either of these is simply xy equals constant. It is trivial to verify that y equals a over x does indeed satisfy the given differential equation. Let's proceed to example 2, which is sin x dy is equal to 2y cosine x dx. It can be observed that the given equation is a variable separable. Thus, we can rewrite it to this form: dy over 2y equals cosine x over sine x dx. Step 2. We now integrate both sides of the equation. We then arrive at ln y equals 2 times quantity ln sine x plus c. Then, converting it to its exponential form, we have e to the ln y equals e to the 2 times ln sine x plus c. We'll now check if our answer is correct by differentiating the result. Therefore, we have y prime is equal to 2 sine x cosine x. To incorporate y, which is equal to sine squared x, we multiply the equation by sine x over sine x, therefore arriving at dy over dx equals 2y times cosine x over sine x, which is the original equation. Therefore, our answer is correct. Our third example is y prime minus y over x plus y squared over x equals 0, which is again a variable separable equation. We can write the equation in this manner. dy over y minus y squared equals dx over x. Then we proceed to the integration of both sides. Now the left side of the equation requires partial fraction in order to be integrated, which we have negative 1 and positive 1 as the constants of these partial fractions. After such integration, we get ln of y plus 1 over y equals ln x plus c. Converting it to its exponential form, we get e to the ln of y plus 1 over y equals e to the ln x plus c. After making the necessary simplifying, we arrive at y plus 1 over y equals xc. For our fourth example, we have cosine x plus y dx plus 3y squared plus 2y plus cosine quantity x plus y dy equals 0. We can see from the given equation that it is again exact. We check for its exactness by letting m and n as the first and second terms respectively. Taking the partial derivatives, we arrive at negative sine of x plus y for both of the terms. Thus, the equation is exact. Step 2. We have u equals integral of m dx plus ky. After substituting m from the original equation, we arrive at u equals sine of x plus y plus ky. Next is finding the value of constant ky by differentiating u from the previous step and equating it to n from the original equation. We then arrive at the answer u equals sine of x plus y cubed plus y squared equals c. For our fifth and final example, we have a word problem. Given an amount of a radioactive substance, say 0.5 grams, find the amount present at any later time. Please note that the experiment shows that at each instant, the radioactive substance decomposes and thus decays in time proportional to the amount of substance present. Now we are given an initial value, which is y of 0 equals 0.5. We denote the amount of the substance at any given time by y of t. Its rate of change is dy over dt equals y prime of t is proportional to y of t, which gives us the ordinary differential equation dy over dt equals negative ky. The minus sign indicates a decay in the substance. For exponential decay, we have a general solution of y of t equals ce to the negative kt. Using our initial condition of y of 0 equals 0.5, we find that c is equal to 0.5. Substituting this to the general solution, we obtain y of t equals 0.5 e to the negative kt as our particular solution. I hope you learned something during this tutorial that can be of use to you. Until next time, thank you and have a pleasant day.